Let us prepare alkyl halides by using first method from alkenes. Roman number 1 from alkenes. From alkenes. Within the bracket, electrophilic addition reactions. We cover basics of reaction mechanism of first year also parallelly, okay? Because if we know electrophilic addition, then you can understand this preparation method. So within the bracket I am writing electrophilic addition. Electrophilic addition reaction. Electrophilic addition reaction. Right. First I will take one simple example. Ethene when treated with the HCl we will get alkyl halide. Okay, one H will be added here and Cl will be added here. Then we will get CH3, CH2Cl. This is a simple preparation method of alkyl halide from alkane, right? Let us see the mechanism for it, right? Mechanism and what is formed as intermediate in the mechanism, let us see. Okay, for this we are going to write a mechanism, keep heading, and that mechanism comes under electrophilic addition reaction of first year. Clear? Right. First one, split HCl. HCl dissociates into H plus and Cl negative. Okay, H plus and Cl negative. See, H plus is electrophile and Cl minus is nucleophile. This is electrophile. Electrophile is represented as E positive. Electrophile. Okay, and Cl negative is the nucleophile. Right. See, in the step 1, see what I am writing. Step 1 is the formation of carbocation. Formation of carbocation, or you can consider this step as addition of electrophile. Addition of E positive. E positive stands for electrophile. Formation of carbocation or addition of electrophile. Okay, right. Before that, I'll ask you one question. You tell me, if I shift pi bond towards first carbon will get which charge? Positive or negative charge? First carbon will get negative because you are shifting the bond towards first carbon. Second carbon will get a positive. Second carbon will get positive. Remember this. Okay, simple basic idea. Right. So I'm taking alkene. And see what I'm doing. I'm adding electrophile first. First electrophile is adding. See, HCl is dissociating into H plus and Cl negative. Why we are adding preferentially H plus to alkene? And why we are calling this reaction as electrophilic addition reaction? Which reaction? Addition of HCl to alkene. We took this one. This is electrophilic addition reaction. Type of reaction also very important. Clear? Why we are calling this as electrophilic addition? Why we cannot call it as a nucleophilic addition? Why cannot we add Cl negative? Let us see. H plus is electrophile, electron deficient species. Pi bond itself is considered as electron rich area because pi bond is formed by lateral overlapping, sideways overlapping, that is loose bond. Okay, it breaks easily and this site acts as an electron donor. This site, pi bond or triple bond, double bond, triple bond, acts as electron rich areas, electron denser areas. Clear? So this is electron rich area. Towards electron rich area, electron deficient species will go. Clear? Got it? For example, if I add Cl negative, if I try to add Cl negative first, Cl negative and this is also negative. This is rich area. So how it is possible to add negative repulsion takes place? So first we add electrophile only. That's why we call this reaction as electrophilic addition reaction. Right, let us start the mechanism. See what I'm doing, first I'm shifting this pi bond towards the right side carbon, okay, then right side carbon will get negative charge. Just now I given one general example, right? So now at present this is having negative charge. Why? Because you are shifting the bond towards this right side carbon. Right side carbon will get a negative, and this H plus will go towards, because this is having negative, so H plus will go towards that carbon only, right? After that, CH2 positive, this carbon will get a positive charge. Why this will get positive charge? Because it is losing the bond. See, it is losing the bond. CH2 and one H is coming, so CH3. So carbocation is formed. This idea is very important in the electrophilic addition reaction of alkenes. The intermediate is carbocation. Okay, carbocation is formed. That's why I wrote first step as formation of carbocation. Clear? Is it okay? Any doubt on this? Right. Next, let us see step 2. Step 2. Attack of nucleophile. Attack of nucleophile. See, I am taking that previous carbocation. I am taking this here. CH3, CH2 positive. Or you can take like this also, ulta. A, B, B, A, both are same only. 2 into 3, 3 into 2, both are same only. So you can take CH3, CH2 plus or CH3, CH2 plus, like ulta. Anything is correct, no problem. Cl negative. CH3, CH2, Cl. So this is the mechanism of preparation of alkyl halide from alkene. Why it is important to learn mechanism? I'll show you, right? Okay. Let us go to very important example, most frequently coming example. I'll ask you one question. Can you try where Cl will be added? Just try. I'm giving the numbering. See here another point I wanted to tell you. Its name also very important. First of all, give its name 3-methyl 1-butene. 3-methyl 1-butene is the name. Name also very important. Can you say where Cl negative will be added? Where H plus will be added? Guess. Any idea? First, second, third, fourth. Actually, addition will take place at double bonded center only. Just one try. Just try. Guessing only. Okay. And Cl negative? Second. Because based on the previous mechanism, right? Correct only. Yes, 99% students will give the answer like that only, because based on the previous mechanism, clear. But you are going to learn some new phenomena, clear. In the second year, you will learn some different phenomena, not like first year. First year organic is very simple and straightforward, but here we will discuss different phenomena. Let us see. I am saying Cl negative adds to third carbon. Third carbon, how it is possible? Actually, third carbon is not double bonded carbon. One rule is there. Always you have to add the atoms to the double bonded center only, to unsaturated center only. Addition takes place always at a unsaturated center only. But why I am adding chlorine at third position? Reason is there. First I will write the product, then we will go with the mechanism. Clear? Look at this. I am giving numbering. 1 2 3 4. At third carbon Cl is added. Let us see the mechanism. Remember, simple questions never come. Okay, rearrangement based, fairing expansion based questions, stability based questions, carbocation stability based questions will come. The very important example already we did this question, means this model question in the alkenes chapter in the first year, but a large gap came now due to IP, so you may forget. No issue. Let us start the mechanism. Take this reactant or substrate, you can call it as reactant or substrate, your wish. Take the reactant, electrophilic addition now. So first electrophile addition takes place. See the pink color one. Pi bond is shifting towards the terminal carbon. Terminal carbon will get a negative charge, so towards that negative, this positively charged hydrogen will go. Clear? Same step like previous. Next, CH3 CH positive CH3. Okay, carbocation formation. Step 1 is the formation of carbocation, but every time you no need to write. Clear? After practice you will write the product directly within a single step. Clear? No need to take step 1, step 2, step 3, but it takes some time, but you will achieve that step. No need to worry. Right, Meenakshi, can you tell me its stability, not stability, order means degree. Which degree carbocation this is? 2 degree carbocation, right? This is 2 degree carbocation. Okay, now you are learning one new phenomenon, new step, right? I am including another step here, a rearrangement step. Rearrangement of carbocation. I'll tell you when we consider rearrangement, what is the meaning of rearrangement, why the rearrangement takes place. Okay, right. I am taking this carbocation here as easily. Okay, but see what I am doing. I am writing H down. Here one hydrogen is there now. Write that hydrogen down. Okay, and CH plus and CH3. So we are taking carbocation which is formed in the previous step, right? Okay. See, this is 2 degree carbocation. You only set 2 degree carbocation. You know degree of carbocations, the order. 3 degree carbocations are more stable than 2 degree. 2 degree are more stable than 1 degree. Clear? Right. Now onwards, throughout organic chemistry, in any reaction, if carbocation is formed, then check for rearrangement. Rearrangement means rearranging the atoms or groups from one place to another place to achieve higher stability carbocation. It is the phenomenon of changing the atoms, changing the position of atoms, or rearranging the atoms or group of atoms from one place to another place to achieve higher stability carbocations. Right here, look at this. I am representing carbon hydrogen bond with 2 pink color electrons. Pink color. These 2 pink color electrons belongs to carbon and hydrogen. Right. One pink color electron belongs to carbon, another pink color electron belongs to hydrogen. Now see what hydrogen is doing. Hydrogen is taking its own electron and electron of carbon also and shifting as H minus towards that carbocation. I'll tell you why it is happening like that, like this. Clear? Look at this, how I wrote the arrow. That arrow should include 2 electrons. Clear? Don't leave 1 electron, include 2 electrons, right? Means hydrogen is taking its own electron and electron of carbon also. You have two pink color electrons, right? See this. So hydrogen is taking its own electron and electron of carbon also. That's why hydrogen is getting negative. Why hydrogen is getting negative charge? Because hydrogen is going along with its own electron and electron of carbon also. Clear? Right. CH3C CH3 positive. Why I am writing positive charge? Can you guess why I am writing positive charge here? Why I am? Yes, carbon is losing its electron. This carbon is losing its electron. That's why it will get positive charge. Now observe its degree. 3 degree carbocation. Clear? So that is the reason. That's why hydrogen is shifting along with the extra electron as H minus. Clear? So this is 3 degree carbocation. 2 degree carbocation, 3 degree carbocation. This is stable. Very important phenomenon. Throughout organic chemistry, remember one point. Whenever you get carbocation, check for rearrangement. See, in all cases we do not do the rearrangement because after rearrangement also sometimes we'll get same degree carbocation. In that case, no need to do the rearrangement. When we do the rearrangement, if there is a chance to get higher stability carbocation, here chance is there to get higher stability carbocation. Clear? Right. So one extra step is over, that is a rearrangement step. Next step is direct addition of nucleophile. Add Cl negative to this carbocation over. Okay. I'm adding here only directly instead of taking another step. Okay, because I explained briefly in the last step. So I'm adding Cl negative here. Cl negative. Addition of nucleophile. The Cl negative adds to carbon with a positive charge. Okay, then we will get 3 degree alkyl halide. Most important reaction in 2 lessons. What are the 2 lessons? In alkyl halides of second year and in the alkenes chapter also. This same reaction can be considered as the chemical property of alkene. See, in organic chemistry, this is only the fetching. One reaction will come in more than 1 lesson, 2 lessons or 3 lessons also. Clear? Same reaction. This concept is used in the alkenes chapter also. Clear? Under chemical properties of alkenes. Right. Which degree alkyl halide you got? You got 3 degree alkyl halide. Clear? So you will get IUPAC name. What is the IUPAC name of the alkyl halide? When HCl is added to some 3-methyl 1-butene, like that you will get the question. Clear? Right. Shall we go to another example? Right. This is also important example. Second example. CH2. Names are very important. Can you try its name? Can you try its name? Its name, because sometimes you will get the names instead of a structure, you will get the name. Try its name. At third position, we have phenyl group. Phenyl. Benzene, when present as a substituent, we call it as a phenyl. 3-phenyl propene. 3-phenyl propene. This is the parent chain here. Remember, this is parent chain and this is substituent. So 3-phenyl propene. 3-phenyl propane. 3-phenyl propene when added with HCl, where Cl will be added and what is the IUPAC name of the formed alkyl halide? Okay, let us see. Cl is adding like this. This is the product. 1-chloro 1-phenyl propane. 1-chloro 1-phenyl propane. 1-chloro 1-phenyl propane. Names also very important. Okay. 1-chloro 1-phenyl propane, 1 chloro 1 phenyl propane. Let us see the mechanism and let us check whether rearrangement takes place or not. I'll take separate page. See here, as usually splitting of HCl is common. HCl dissociates into H positive and Cl negative. Okay, this H plus adds to unsaturated center. Look at this. I am shifting this pi bond towards terminal carbon. Okay. Terminal carbon will get negative charge. Towards that negative, H plus will go to form carbocation. Look at this. CH2 CH positive and CH3. See the degree of this carbocation. This is 2 degree carbocation. 2 degree carbocation. Okay. After rearrangement, is there any chance to get higher degree carbocation? And is there any necessity to do the rearrangement here? In this case, will we get a higher degree carbocation or will we get same degree carbocation? Can you try? Which degree carbocation we will get? Which degree carbocation we will get? Secondary. So is there any necessity to do the rearrangement? Again you are getting 2 degree. But we will do rearrangement. Or how? We are getting same degree carbocation. Again why we are doing the rearrangement? Means we will do the rearrangement to see here. Observe this carbocation. Clear? This is 2 degree carbocation without resonance. 2 degree carbocation without resonance. Resonance is not present. Without resonance. Clear? Once again I will revise structural requirement for resonance. This is first year topic. Look at this. When double bond is connected to A with a positive, A is any atom, mostly like a carbon, A with a positive or negative single electron, lone pair or another double bond. In that case, resonance is present. Resonance means resonance effect means shifting of pi electrons or non-bonding electrons. Let us see one example. In this case, resonance is present. Very easy to identify the resonance. See, if positively charged carbon or carbon with a positive is connected to unsaturation center directly, unsaturated center directly, in that resonance is present, then you can shift the electrons like this. This carbocation is stabilized by resonance because pi electrons are going towards this carbocation. This is deficient, right? This is deficient. This carbon is deficient. So pi electrons are going and it will get stability. It is deficient. If it gains electrons, it will get stability. This carbon. Clear? So this is structural requirement for resonance. Again, we will do in the revision class. Okay, right. Remember this condition. When resonance takes place, if positive charge is connected to the double bond directly without any atom in the middle. For example, see, if I write like this, in this resonance is not present. In this resonance is not present because between double bond and a carbon with a positive, some other atom is there, CH2. Here resonance is not present. Clear? Direct attachment should be present. Here direct attachment is not present. This is the same situation. See. Clear? Here double bond is present, here carbocation is present, in the middle CH2 is present. Clear? So there is no resonance. So 2 degree carbocation without resonance. Now let us see what happens if we shift the hydrogen. I am taking this as Stiesling. But I am writing this CH2 like this, CHH. CH, H, CH positive and CH3. Now hydride ion shifting takes place. Right. See, 2-degree carbocation, 2-degree carbocation without resonance. This is 2-degree carbocation with resonance, benzene ring resonance. 2-degree carbocation with resonance, more stable with the resonance. More stable because the resonance effect is present. Resonance is present. Clear? Look at this. This pi bond is connected to carbocation. So resonance takes place. Adjacent, both are adjacent only, na? So resonance takes place. So this is more stable carbocation. Sometimes you will get same degree, but other factor is resonance. Resonance is present. Clear? Very important question. This is also. Okay. In the next step, Cl negative will be added. So I am adding Cl negative directly to this. Are you getting Meenakshi? Is everything okay? Right. Meenakshi, see, we are shifting H minus, right? Sometimes another atoms or group of atoms shifts. Okay, based on the given structure. There is no mandatory condition to shift H minus always. Sometimes methyl shift also will take place. Clear? Let us see one example for that. Under preparations only, see how much depth we are going. Clear? We are doing preparation methods only, but with a different approach. Look at this. Cl will be added here. This H will move this side. CH3, CH3 here. Cl will be added. CH3. Names are very important. What is its name? Give the name for this. What is its name, Meenakshi? 1, 2, 3, 4. 1 butene. 1 butene. Yeah, 1 butene. 3,3 dimethyl, 1 butene. 3,3 dimethyl, 1 butene. 1 butene. And its name is, we'll go like this, 1, 2, 3, 4. 2 chloro, 2, 3 dimethyl butane. 2 chloro, 2, 3 dimethyl butane. Let us see the mechanism for this also. See, H base adds to this carbon. See, you no need to take one first step, second step, third step. You can do directly. Okay. See, this is which degree carbocation? 2 degree. Methyl shift takes place. Methyl shift. Because your hydrogen is not there. So methyl shifting takes place. Methyl group also will shift along with the bond pair of electrons. Clear? Methyl group takes its own electron and electron of carbon also to get 3 degree carbocation. This is 2 degree, this is 3 degree. You know in the next step what happens? Guess in the next step what happens? What happens in the next? Cl negative addition takes place to get the product. Okay, let us consider it as A. I am writing here A. Okay, A means this one. Clear? So sometimes methyl shift also takes place. I covered that also. But remember one thing. Sometimes we'll get bond line structures. Don't get confusion. See, for this, what is the bond line structure? Look at this. Like this. Okay, don't get confusion. Both are same one. Both are same one. Mostly bond line structures will come. Okay. Another one. Similar to this rearrangement, another important phenomenon is there. Under the preparation of alkyl halides only, under the first method only. Okay, we are under the first method only. We are preparing alkyl halides from alkenes only. Clear? Next. See another concept, ring expansion. Ring expansion. When paper is very tough, okay, then you will get these type of questions. Luckily, let us see. What is the ring expansion? What is ring expansion? We are preparing alkyl halides, okay, from alkenes. The product is 1-chloro-1-methyl cyclohexane. Once observe the ring size. Ring 1, 2, 3, 4, 5 carbon. This is a 5-member. Here 1, 2, 3, 4, 5, 6-member. 5-member ring to 6-member ring. First of all, you should understand which member ring is stable, which member ring is unstable. Clear? Look at this. 3-member ring, 4-member ring, 5-member ring, 6-member ring. This is the stability order. 3-member ring is unstable because of bond angle strain. Actually, see triangle. Look at this. The angle is very less. Bonds are very close to each other. Like this. See, bonds are very close to each other. As ring size increases, bonds will expand like this. Means angle between them increases. Now angle is less. Now angle is more. Right. If angle is more, then bonds will move away with each other. Then repulsion decreases, stability increases. Here bonds are close, so unstable. So 3-member ring, try to convert it to 4-member ring, 4-member ring, try to convert it to 5-member ring, 5-member ring, try to convert it to 6-member ring. So this is 5-member ring, it converted to 6-member ring due to stability reasons. 6-member ring is stable. Clear? And let us go with mechanism. See the mechanism. Same step. Correct only, Meenakshi? Any doubt in this? Is this step okay for you? Meenakshi? Are you comfortable? Are you getting any sleep, Meenakshi? Okay? Our picture can we discuss tomorrow morning? Are you okay? Yeah. No. I thought that you are getting sleep something because late night. Okay. I am taking this and giving the name as a ring expansion step. Ring expansion step. Take this carbocation. Meenakshi, just look at this. Stop writing. If you are writing, then stop and look at this pink color bond. Observe this pink bond. Just I'm representing this bond as a pink color, and white dot represent carbon atom. That carbon is surrounded by 3 bonds, and another hydrogen also present here, but generally we do not represent hydrogen atoms, right? Here hydrogen is present. Now what I am doing, this white color carbon, white dot is connected to 4 bonds. One is invisible hydrogen, second, third and fourth bond is pink bond, right? Now what I am doing, I am removing the pink bond, detaching. For example, see, this is white carbon, pink bond is attached. I removed that, I detached, right? The bond is detached and attached to carbocation. Remove the bond and attach to carbocation to get a higher membered carbocation. Dash 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 arrow mark. Now observe, just a second, don't write anything. Now white dot means white color carbon will get a positive charge. Why it will get positive charge? Because it is losing its bond. Clear? Need to get this step, Meenakshi? Electrons? Yeah, this bond, yes. This bond will attach to this carbocation. See, this is carbon, pink bond is connected. Remove that and attach to another carbon. Okay, along with the bond, electrons will go. Clear? When you detach the bond, in this bond 2 electrons will come. Carbon electron also comes into this bond. Clear? That's why carbon is getting positive charge. Clear? Got it? No, not rearrangement. This is 5-member ring, na? Okay, kind, but particularly it is called as ring expansion, because clearly we can see 5-member is converting into 6-member. Give the numbering for this. 1, 2, 3, 4, 5, 6. Clear? So this is 5-member only. 5-member is converted to 6-member. Clear? A kind of rearrangement only, but that word is dominated by this word ring expansion. Clear? Because clearly we can observe the change, size, ring size. Clear? Again rearrangement takes place. Next step is rearrangement only. Ring expansion, rearrangement parallelly takes place. Clear? Now let us draw this ring in the proper format. See, 6-member ring. So I am writing that in the proper format. OR means this can be represented like this. First give the number 1, 2, 3, 4, 5, 6. At first carbon what is present? Meenakshi. At first carbon what is present? One line methyl. So CH3 methyl. At a second carbon, positive charge. Carbocation, positive charge. Right? So 6-member ring is formed. That's why heading is the ring expansion step. Now again rearrangement takes place. Rearrangement. Take this carbocation as it is. Here hydrogen is present, right? Hydrogen is present. Hydrogen moves along with the bond pairs. positive charge. 3 degree, this is 2 degree, this is 3 degree carbon. Clear? Now Cl negative attack takes place.